Great. So welcome to another class about the Branch spaces. And today's class, I'm going to present a application in number theory related with the zeta function. So basically, this will be an application of the theory of beta-Wiener spaces in analytic number theory. So before I start, I have to recall the main mathematical objects of this class. And the most important one is the Riemann zeta function. So it's the Riemann zeta function, which is a well-known function of a complex variable S. And this series will always converge if the real part of S is greater than 1. Okay. And just a quick remark, today I am in my office, so perhaps my writing has a bit more of a delay than what it used to be. Okay, but anyway, so that's the zeta function. And what we know about it, well, this function is important in number theory because of its relation with prime numbers, okay? So let me write that. So the zeta function is very important in number theory for several reasons, but the most important one is the relation with the prime numbers. Okay. So what you can show is that, for instance, the zeta of S equals the product over all the primes P of 1 minus P2 minus S. And that also will work when the real part of S is greater than 1. And that's the famous Euler product for the zeta function. So you already see the relation with primes here, and there are further relations even more important than this one. What do we know about the zeta function? We know that zeta of S extends as a analytic function in the whole complex plane minus the point 1, where the series doesn't converge, and in there you have a pole. Of residue. You can even compute the residue, and you see the residue at a pole is 1. So then we can define the Xi function, and then after some computations, S minus 1, pi 2 minus S over 2, gamma S over zeta of s. Then after some computations, you can show that Xi is entire. So you just removed all the singularities. For instance, the pole at the point 1, you just removed. And then you can show the functional equation. Xi of s equals Xi of 1 minus s. That's it's called a functional equation. Okay. And this is the way you by defining these Xi functions, this is the way you extend a zeta to the whole complex. One of the ways you extend zeta to the whole complex plane and prove this fact here that I stated. Okay. And then we have the Riemann hypothesis. Let me remind that. So what's the Riemann hypothesis? Well, before I say what the Riemann hypothesis is, let me just make some quick remarks. So the first one is that, well, by the product formula, the formula involving primes here, we know that zeta of s is not 0 if real part of s is greater than 1. Okay. By the functional equation, by the fact, the second point is by the fact that Xi of s is entire. So you look for the formula of Xi, you see that there is a gamma here times the zeta, okay? Well, gamma has poles at negative integers, less or equal non-positive integers, let's say. So when you divide it as by 2, you will have a problem at the negative even integers. At the 0 you won't have because you have this s multiplying here. Okay, so this would explode at the negative even integers. So therefore the zeta function has to have a 0 there. So by the fact that this is entire, we have that zeta of minus 2n is a 0, and these are called the trivial zeros. I mean, not so trivial at first. Once you define just zeta at first as a sum, it's not so trivial to verify that it extends and these are zeros, but the functional equation gives that for free. And also one can show the zeta of 1 plus it is never 0 for all t real. Okay, so you have a vertical line with real part equals 1, and in the vertical line zeta is not 0, and that bit is actually equivalent This is statement that the zeta is not 0 in this vertical line is equivalent to a prime number. Theorem. That is that the number of, which is the number of primes up to x is asymptotic to x log x. Okay, and one way to see that is that have this so-called explicit formulas. Let me continue the parenthesis. And this is because of the explicit formula connecting, whenever explicit formula in number theory, some formula that connects the zeros of zeta with prime numbers, roughly speaking. And the explicit formula we have here is that the prime counting function times log of x is roughly as x minus the sum of x to the whole divided by whole minus some log 2 pi, with the whole are the zeros of zeta between 0 and 0.5. The real part of whole greater equal to 0, less equal between 0 and 1. Okay. So so if I don't have a 1 here, if the real part of this guy is always strictly less than 1, then the behavior of this sum should be something like 1 minus epsilon. So the behavior of this whole thing when x goes to infinity should be basically like x. And since this thing is pi of x, a prime counting function, so the prime number theorem, the statement that this behaves like x over log x, is the same as the statement that when you multiply log x by the prime counting function, by this function here, you just get a behavior like x. And so if we show that the zeta is never 0 on this line, then that would imply, I mean, you have to have some technicality of a comment, of course, but that would imply the prime number theorem and vice versa. Okay. So these are the basic stuff. And so the Riemann hypothesis is the statement that all zeros of zeta of S in the critical strip are aligned. Because I have, so that's the Riemann hypothesis. So the usual picture that everybody does, I will do as well, is to draw the critical line. This is 0, this is 1, this is real part equals a half. All the zeros in this region should be aligned in the middle of the strip. Okay, so that's the Riemann hypothesis. So what I want to talk about today is we assume the Riemann hypothesis, which is often what people do in analytic number theory, because, well, it's a very old, open problem, and nobody knows how to solve yet or have a clear strategy how to solve it. So, I mean, a bunch of people, as we sometimes have to assume the Riemann hypothesis and just conclude some statements. And we will do that in this class. So there is an old result of Littlewood, which is I want to talk about today. So Littlewood in 1924, he proved that that under RH, so assuming the Riemann hypothesis, we can give a very nice upper bound on the behavior of the moduli of the zeta function on the critical line, okay, how it grows. And he showed that this is supposed to be less or equal than some constant A, times some other constant p log t over log t as t goes to infinity. So as I'm going in this direction in the critical line, and measuring the absolute value of the zeta function, it should grow like this, okay? Just as a side remark, there is, which I won't write, there's the Lindelof hypothesis, which states that which should have something like c epsilon t to the epsilon as t goes to infinity for every epsilon you give me, okay? And this is not under the Riemann hypothesis. It should be like this. People find it very hard to show, but the Riemann hypothesis implies the Lindelof hypothesis. So the Riemann hypothesis would imply this because, well, we just saw it. Later would show this bound under the Riemann hypothesis, which would imply this one. But anyway, this Lindelof hypothesis seems something easier to show, and people without the RH, and people try to do it, and there are a bunch of papers trying to put the smallest possible constant in this epsilon here. And I think the best one is a paper of Bourgain of 2017. But anyway, that's just a side remark about the relation of the Riemann hypothesis of this Littlewood bound with this. This is the Lindelof hypothesis. Okay. Any questions so far? Okay, so
none of
yes.
Sorry, none of this has been proven in this class yet. Are we going to, or are we just going to accept all the facts here?
Well, the things that I'm saying right now, yes, we're going to just assume and just remember, let's say, recalling you what the basic objects I'm going to deal with, and then I'm going to state the main theorem of this class in a moment.
All right. Thanks. That was no criticism. It might have sounded a bit like it, but sorry. It was just because I was curious about some of the proofs. But yeah, I can read them somewhere else.
Yeah, yes. Well, I mean, some we did in the seminar in analytic number theory, but not this Littlewood. We're going to do the Littlewood one anyway. But the other stuff, the explicit formula and this the definition of zeta, yes, we're just going to assume. You can read in Wikipedia, or you can go to my teaching page, and then you go to the seminars at analytic number theory. There is a files named notes there, and then you can download. There are a bunch of notes there about from the students in this class I gave last year. Anyway, so what's the question we want to address today? The question is the following: what is the smallest? So once we know that under RH, that's the best we can do. Okay. By the way, this is not the conjectured bound. People conjecture that should be slightly better, but well, this theorem is since 1924, so it's almost 100 years, and nobody could improve this asymptotic here. So this looks like a very, even assuming, all right, we are assuming anyway. So we're not going to improve the asymptotic because it's surprisingly hard, but we can improve the constant here. So that's the question I want to address today. What's the best? B, we can put. Okay. And this is a paper of 2009 of two big names in number theory, Chandy and Soundararajan. Soundararajan would be the biggest one. It's Professor Stanford, very well known in number theory. And the theorem is the following. And I will mention what the paper is in a moment. So following my number, it should be H. So theorem H should be that zeta of a half plus IT is, let's say, equal to A e to log 2 over 2 plus some little o of 1, meaning that when t goes to infinity, this goes to 0, log t divided by log t. Okay, and this is the current best bound. So this is a paper. So this is a paper from 2009 called bounding zeta of a half plus it on the Riemann hypothesis. This is 2009 by Shindy and Sound. Okay, that's the current best bound, and people even think that it would be pretty hard to beat this bound. In a way, in the proof that I'm going to present, you will see that there isn't much room for improvement. I mean, you do whatever you do, basically the best you can possibly do, and then you get this. Okay, so the main part, so the rest of the class, I want to prove this result, and this would be a very nice application of Pillai-Vinet spaces. Okay, so the proof, I divided the proof in several steps. And you stop me whenever you are you have a question, etc. The proof is pretty much self-contained, but other than the information I just gave you, maybe just one bit more or 2 bits of information about a number of theoretical part will be needed, but not much more. Okay, so step 1. So step 1, I want to derive some asymptotic formula for this, even if it's pretty hard, something that I can understand in some way. Okay, for instance, a formula that would be a certain sum of over, let's say, it's the zeros of zeta, because then for the zeros of zeta, I have a much better control than just working with zeta. So that's what we'll try to do. So, so the piece of information, number of theoretical piece of information is the fact that the Xi function is a function of order 1. Okay, so the Xi has order 1. Okay, which means that is a function that basically grows as an exponential of the moduli of S to 1 to the power 1 plus epsilon, let's say. And therefore, it would have its a Hadamard factorization of this type. Okay, so this is a basic result in complex analysis. Whenever you have a function of order 1, you will have a Hadamard factorization of this type, and I will always denote whole to be the non-trivial zeros of zeta. That means the zeros in the critical strip. The Xi function only has those zeros because we have eliminated all the trivial ones by, let me go back and recall, by multiplying by this gamma, we have removed all the trivial zeros of the zeros here. So we only have those zeros inside the critical strip for the function C. Okay. And then once you have this, we can just do a computation, and then you can realize that and after some computation, we can compute what this B should be, and this B is actually minus the sum of the real parts of 1 over whole. Okay. Okay, so this is the piece of information from number 3 that I need. I will need just another one later on, but this is the first one. To show that xc is a function of order 1 is actually not that hard, because zeta is well behaved when you have a summation, and in gamma would be we have order 1 as well, so it would be, it's not that hard to show. It has order 1. Okay, so what I'm going to do now, I'm going to do a certain trick, and there is no real reason why I'm doing this trick. It's just that it works. I'm going to compute this moduli again. Okay, and these numbers here, a half is the stuff I want to compute anyway, but this 3 halves here is just because it works nicely. It could be another number. In the end, if things would cancel, etc. So the choice of this guy is not that important. So let's see. So I have a product formula. I can just write what it is, and then you do the computations. We'll have this a half here and have this minus 3 halves. So in this bit here, I'm just going to have e to 2b. The imaginary part will go away. And then we're going to have like the product whole over the zeros. And then we're going to have like 1 minus s whole. And then, oh, sorry, it should be 1 plus half plus it over whole. And then 1 minus 3 halves plus it. In moduli, and then we're going to have what? We're going to have this e to a half plus it over whole, and then I'm going to divide, and take the moduli as well. Then I'm going to divide by what? I'm going to divide by 3 halves minus 3 halves plus it over whole. So the imaginary part of the t will cancel. This is nice. So this t here will cancel with that guy there. And then we're going to have a half plus 3 halves, which is 2. So it's going to become just 2 over whole. But I'm going to take the moduli, so the real part. So in the end, by doing some magic, we get just e to 2 real part of 1 over whole. Is that, yes. Okay. We can also simplify the stuff here. So let me continue. So rho, I'm assuming the Riemann hypothesis. So we write rho always as a half plus I gamma, because I'm assuming RH. Oh, I shouldn't state that in the theorem. So let me state that. Okay, you have to assume RH. So I'm assuming RH, so the zeros of this form. So then I can move on and do, so this bit here, when I take the product of this whole thing here with this guy, and then I use this formula here, we cancel with that guy here. So you can cancel this part with this part. That's why we're choosing these numbers as well, because it will help in this way. And then we can just write what the 0 is and do the computations, and you will get this thing. Okay. So this is the formula we got. So now what I want to do is I want to take the logs on both sides. So when I take the log here on the right-hand side, it's going to be a sum. Then what you're going to do is when I'm going to put a square here, and then just take a root on the outside. And then when I'm taking the log, I'm going to have a half, and then I'm going to have a sum. Okay. So the sum should be the log of the moduli squared of the stuff inside, which is going to be this, and then 4 plus gamma minus t squared. But I want to reverse that, so I want to put the minus. So I put the minus here and reverse. So 4 plus gamma minus t squared over gamma minus t squared, which I want to write as ft minus gamma. Is that how? Yes, the sum over gamma. So the sum over the imaginary parts of the zeros of the zeta function on the critical line. Okay. So nice, I have a sum over zeros, which is what I wanted in the beginning. Now I have to estimate these things here. Okay, so let's estimate these things. And then I'm going to use the fact that xi of s equals xi of 1 minus s. So then xi of minus 3 halves plus it equals xi of 5 halves minus it. Okay, so then I'm going to estimate these two guys. So then this thing here would be log of, so let me also write, so write s as a half plus it, and then, well, 5 halves minus it will be 2 plus s bar. So that would be 5 halves minus it. If I write s in this way, okay. So then this bit here will be what? Will be zeta of, will be, sorry, xi of s divided by xi of 2 plus s bar. So let me write using the formula for xi what this is. So we're going to have a halves, which we will cancel. We're going to have s minus 1, pi minus s over 2, a gamma s over 2, and a zeta of s. So remember that this is the bit we want to bound, because s is a half plus it. Log here on the outside. And below we're going to have a 2 plus s bar, a 1 plus s bar, pi minus, that would be 1 minus s bar over 2, gamma of 1 plus s bar over 2, and then a zeta of 2 plus s bar. Okay, so that's the computation we have. And then, well, I'm always imagining t going to infinity. So always keep that in mind. So t is going to infinity. Okay. So this log here will, of course, be split as a sum of things. So what happens with the first term? So let me maybe color. So the first term would be this bit. The second term would be this guy. The third term would be this other guy here. And the fourth term would be this other guy there. So in the first term, you just have like a quadratic polynomial divided by quadratic polynomial. Both are going to infinity, like t. So this would be basically just a O of 1, okay? And is this bounded by a constant, which I won't care. The second term is exponential, but I'm taking the moduli. So once I take the moduli, I want to get in the real part. And the real part is always bounded. Oh, my 5 here looks like a S. This is a 5. And the real part is bound. It's just a half or 5 halves. So the second bit is also an O of 1. We have the third bit, which I'm writing, which I can write as the real part of the log of gamma of S over 2 divided by gamma of 1 plus S bar over 2, because the real part of the log is just the log of the moduli. plus we have the log of the moduli of zeta of s, which is the stuff I want, minus the log of 2 plus s bar. And that's going to be an O of 1 again, because I'm just going to write this quickly, because if you do log of moduli of s of 2 plus s bar, okay, well, basically zeta of 2 plus s bar, oh, I have a crow in my window. Okay, let me continue. This is going to be bounded. This is basically like 1, okay? So because the real part here is bigger than 1, okay? So I can write this zeta as a sum, and I can send t to infinity, and you see that this converges to a number, okay? So so this is like comparable to some constant. That's what I mean. So it's going to be an O of 1 as well. Okay, so I just have to estimate this bit here, and this I have to use the Stirling's formula. So using which I will recall, what's the Stirling's formula? The Stirling's formula is that the log of gamma of z for any variable z is log of square root of 2 pi. Is this the log of the Stirling formula that we usually use? Plus something that decays like z to minus 1. Plus, oops. Okay, that's the Stirling's formula. So I would put as an exercise that the real part of the log of gamma of s over 2 divided by, oops, it's the log of the whole thing. Log of gamma of s over 2 divided by gamma of 1 plus s bar over 2. Then you use Stirling's formula for each factor. You have a difference, and then you have to take the real part of each part. And that bit here is going to be O of 1 over t minus log t. Okay. Okay. So in the end, what I get is that log of moduli of xi of s divided by xi of 2 plus s bar equals some O of 1 plus log of what I want to measure, which is a half plus it, minus, and then I'm going to absorb this O of 1 over t into O of 1 because t is going to infinity anyway. So I'm just going to have this and then the minus log t. Okay, so in the end, since I had a formula for this in terms of the summation of zeros, which was what I derived a moment ago, we can put everything together and then we derive a very nice asymptotic formula. And this is basically just a very pretty trick, nothing more. And you can see that if you know L functions, for instance, you can see that, well, there's no reason why this can't work for an L function. It actually works for every L function, these kind of tricks. So you get just log t minus a half the sum of half of t minus gamma over the gammas plus some O of 1. Okay. So again, the log of the zeta function should behave like log t divided by log t. So just think of that the zeta function, that's the result. If we take the log, it should just behave as some log of t divided by log t, but log t is so small that you don't care. So it's just behave like log t. That's what you have to keep in mind. So it grows, so in particular it grows, so any O of 1 factor that you have, it's okay. You don't care about it. So this is step 1. Any question here in this computations? See, I know that it may be a lot of information. I don't assume that you follow everything. My point is just follow the main parts. Okay, we had to estimate zeta of a half plus it. You use the Hadamard factorization plus some trick to derive a formula involving zeta and the sum over the zeros of zeta with some special function f, which I even didn't define. I have to define f here. Yeah, so this f here, I mean, you can figure out by the context, but f of x should be log of 4 plus x squared divided by x squared. Bottom line, there is some auxiliary function f, so that you get a function, a formula like this. Okay, and this is coming from the Hadamard factorization. Okay, so step 2. We have just 2 more steps actually, so we're almost done. Maybe I can even go slower. So step 2, so there will be another piece of information coming from number theory. Actually, this piece of information is not really number theoretical. I'm going to present a theorem we state only for the zeta zeros, but actually it works for any zeros of a Poier-Laguerre function. Okay, so and as I said, the C function has this Poier-Laguerre property. So maybe I mentioned in some exercise class, not in the videos, but anyway, it's a very general formula. It's usually only used in number theory, but it works in general. And that's called the Guinan-Weil explicit formula. There are people that don't use the name explicit formula here because there isn't any, it's kind of a general thing, which is not really related to zeta and primes and etc. It would work for any, as I said, any Poier-Laguerre form. Sorry, I said Poier-Laguerre, I mean Poier class. It would work for any function in Poier class. But I will state only for the zeta zeros. Okay. So what's that formula? Formula is the following. So you start with an auxiliary function h, which would be analytic. If h is analytic in a sort of strip, and the strip has to be the imaginary part less or equal than a half, which I would put a half plus. Okay, which means that for some number slightly above a half, the function is analytic in that strip. Okay, and it decays like hc is less or equal than some constant divided by moduli of z 1 plus delta for some delta positive. Okay, so the drawing is you have here a strip, you have here the real line, you have here a strip, and the height is just above a half, so a half plus, let's say, just above a half. The function is analytic in there, and in that strip it decays like power-like, but with some power slightly greater than 1. So this is just an auxiliary function. So then what happens? Then we have an explicit formula for the sum of this function over the imaginary parts of the zeros of the zeta function. So again, gamma here will always be the zeros of the imaginary part of the zeros of the zeta function in the critical line. So what's that explicit formula? We have 3 terms that we separate like this. So it's 1 over 2i, then plus over minus 1 over 2i. And then we have h hat, which is the Fourier transform of h in the sense I defined before already, times a certain constant, which is log of pi divided by 2 pi. That's term 1. Term 2 is an integral, which is h of u, and then the real part of gamma prime divided by gamma at 1/4 plus iu over 2. The u's stay with me, and we'll have still one other term, minus 1/2, and then now a sum over prime numbers, which won't look like a sum over prime numbers, but it is. And in here, the Fourier transform log of n over 2 pi, and then again Fourier transform minus log of n over 2 pi, closed. Okay, that's the Guinan-Weil explicit formula. Okay. Okay, so what you have to, whenever you see a big formula, well, first you have to be very happy because yes, another big formula, yes. At least I am always happy when I see a big formula. But the most important thing is to detect the information the formula is giving, and so you can split it in your brain in parts that have particular aspects. The first one is, well, you have a kind of an evaluation here. So you have evaluating the Fourier transform at 0 and at these points. Okay. And then you have some kind of an integral involving some nasty function. We don't care about, it's just a kind of integral, a weighted integral of the function. And then we have a summation. And I have to explain what the gamma n is the van Mogold function. Function, which is defined as gamma of n equals log of p if n is a prime power, so p to a certain exponent, and 0 otherwise. So indeed, this formula, this sum here is a sum over primes. So we have three terms. The first is an evaluation, the second is an integral, and the third is a sum over primes. Okay. So what I want to do is to use that formula. So recall that in the end, we got this here. Okay, so the object we want to estimate is given by a sum over zeros. So it would be nice if this f was a possible h. If this f was a function like an h function, I could just apply the Guinan-Weil and write this sum explicitly like this. Okay, but I can't, because f, as I mentioned, is some log of 4 plus x squared divided by x squared. It's some crazy thing. So I can't do it. However, I could definitely do it if I come up with some h function that, let's say, lies below my f function. So if I come up with an h that lies below f, okay, I could definitely bound this sum by just above, by log t minus a half, the sum with this h. And now I have a sum with the h, and then I can use the Guinan-Weil thing. Okay, so that's the strategy. Okay, so that would be the idea. So let me write here. So the idea, bound f from below by some admissible for the Guinan-Weil formula. Each. So that's the idea. Okay. How can we do it? So let me state a lemma. And this will be similar to the Hilbert inequalities. Recall that we had a function which was the sine function, -1 if x is less than 0, +1 if x is positive. And I said that we could create a function that lies above and below that function n, which is of exponential type. Okay, that's what we're going to do here. So lemma, let g of delta be a function in Pavlov 1, so means L1 on the line of oh, sorry, I had a problem here. Let me go back here to zone. Change screen sharing. For some reason, it stopped. Okay, let me continue. So Pavlov 2 pi delta. Okay, and let's say delta is greater or equal to 1. Always imagine delta going to infinity together with t. Okay, let's say even. So you have a function there, even delta is greater or equal to 1, and such that, say, we have an inequality like this. For every x in the real line and for every delta, say greater or equal to 1. Okay, so suppose I have a function in the Pavlov space of type 2 pi delta, so the Fourier transform is supported in the interval minus delta delta, which lies below my function f, this log weird log function x, and we also have this lower bound here, and they're all uniform in delta. Okay, this c doesn't depend on delta. Then log t minus a half sum of gamma of t minus gamma which is, well, we can read, right. This is then log of zeta of a half plus it, which would be that sum is going to be less or equal than some constant a plus some other constant b, all independent of t and delta e to pi delta plus 1 over 4 pi integral from minus infinity to infinity of f of x minus g delta of x dx. Okay. So bottom line, if I create a function, in the Pavlov space, which lies below f, and it has also a certain bound here, so it's not too terrible below, then I get a bound for the log of zeta. And these are just numerical constants, this a and this b here. So you see already that, whoa, very nice. Then I have this integral. So if I try to minimize this integral here, I'll make them up with the best possible upper bound within this strategy, okay? So already faced with the problem of finding what's called a minorant of a given function, a target function f, and minimizing the L1 distance to it, okay? But that would be the L1 norm of f minus g delta, okay? So this is what is called one-sided extremal problem in the literature, okay? So let me prove this lemma. Okay. Yeah, it's too good. So first I want to show that G satisfies the conditions for the Guinan-Weil formula. G is admissible for Ginenweil. Okay, so what do we know? Well, note first that, well, f of x is what? Log of 4 plus x squared over x squared. That is less or equal than some constant. It's easy to see that as x squared, because when x goes to infinity, this basically is going to a 0 at a certain speed, which would be proportional to 1 over x squared. So then, and then when x is small, you can bound it by this, okay? So there is a universal constant c that bounds this. In particular, you have that g delta of x times x squared belongs to Paley-Wiener space. Well, it's still of exponential type, which is just multiplied by a polynomial, so the type doesn't change. But now on the line is bounded. Okay. So 2 pi delta. Okay. But then we know what, then we know what? Then we know that g delta of z times z squared, if I take the sup of this thing, let's say on the line imaginary part of z equals, let's say some number theta, this is always less or equal, oh sorry, you have to divide by minus 2 pi I delta z. So recall the theorem that we proved, so I'm using it here, that the function belongs to the Paley-Wiener space. So maybe I should repeat more slowly. The function belongs to the Paley-Wiener space if and only if. So that implies that x squared g delta of x, which you could see. It implies this. So that was the theorem that I proved the last class. Okay. In particular, if you do the sup norm in a horizontal line, it always loses to the sup norm on the real line, another property we showed about Hardy spaces. So this is less than the sup on the real line, and the sup on the real line is uniformly bounded by some constant c, okay? Because we know that g lies below something like this, and other something like this, and this is less or equal than 1 plus x squared, but from some numerical constant c. Okay, so then I know this, okay? Because it loses to the sup on the real line. Write it explicitly, which is some constant c. So that implies that g delta z in moduli is less or equal than some constant moduli of z squared. And then if I move this guy there, it would be just 2 pi delta moduli of y. Okay. So there we go. Now it satisfies the Ginenweil condition. Let me go back and see what's the Ginenweil. It should be analytic. Well, my function is entire. Okay, so h could be g because it's entire. And also it has to decay like something bigger than c to 1 plus delta. And ours actually decays like c to z squared. It should put here to be precise. So z going to infinity. Or maybe like c greater or equal to 1. An imaginary part of z less or equal than 1 plus. Okay, so so that's what we have. So now I can apply the Ginenweil formula for G. I'll actually not apply the Ginenweil for G, but for a translation of G. If G is admissible for Ginenweil, then a translation is also admissible. So that's what I'm going to do. So we know that log T minus the sum. So we know that the zeta was bounded by log t minus the sum of this f plus some O of 1. So I just need to bound this, this bit, the O of 1 part, we don't care. So I just need to bound this. So this would be less or equal than using this function g, it just be that. Okay. So let me not put this log for the moment. Okay. Let me just bound this sum and then the rest will follow easily. Okay. This is the important term. So I can bound by this, and this will have 3 terms because this would be equal to the Ginenweil applied to this guy. So what would be these 3 terms? So that's the Ginenweil. Again, let me recall what the Ginenweil is. So I have a sum. The only difference is I'm doing, I'm applying this, oops, stop. I'm applying this for h of z equals g of t minus z, t delta, okay? That's the only difference. So I have these 3 terms, t1, t2, t3. t1 is evaluation, t2 is an integration, and t3 is a sum over primes. So let me evaluate each one. T1. With T1, well, explicitly, it would be minus g delta of t minus 1 over 2I plus g delta of t plus 1 over 2I minus the Fourier transform of this function here evaluated at 0, which would be the same, which is just the integral. So it would be the same, there would be no translation here. Log of pi divided by 2 pi. Okay, and this is, everything is here is like O of 1. So let me convince you that. Well, first of all, what is this? Okay, well, this I can bound using this formula. Okay, and in here I only get the imaginary part, and the imaginary part here is a half. So this term here will be bounded. Well, you have this delta here, so maybe I have to include this delta here. It won't be a problem, but maybe I have to include this delta there. So recall that I had an exponential here to couple it, so we can include that. And you have a half here, so that would be okay. So this is not all 1, so this should be a bit more. This exponential in the end will be an error term, so don't be worried about it. So this would be something like O of, the first bit would be something like O of exponential of, let's say, pi delta. In here, I would have this t here, okay? But then t is going to infinity anyway, so I'm not just bound that by O of 1. The same bit with the thing on the right, okay? And then what is the Fourier transform of the function? Well, the Fourier transform at 0 is just the integral of the function, but the function is bounded from below and from above on the real line. Recall again that this is bounded by some other constant like this. Uniformly, it doesn't depend on delta. So that term would be an O of 1. Okay. Any questions here in this bound? I mean, if you spot something wrong, please stop me. Let me bound T3 now, because T2 is the integral term, and that would be a bit more complicated. Not that much, but let me bound T3 first. Okay, so what's the term T3? Let me write it explicitly. T3 is something like 1 over 2 pi, the sum greater or equal than 2, the Van Maughold function, and then h delta hat, log of n over 2 pi. Well, this h here would be, let me define. So what is h? H delta z should be g of delta of t minus z. Okay. My log is terrible. N over 2 pi. Okay, that's the term. Great, well, I have to do the Fourier transform. When I apply the Fourier transform here, I will get just a exponential times the Fourier transform of G. So if I put the moduli inside, if I do this, the Mogul function is always positive, so I can do this. And put the less or equal. Okay, and then I can replace this by G, because when you compute the Fourier transform of H delta, it would just be a modulation times the Fourier transform of G, which will have norm 1. So I can just do that, okay? And then what's the Fourier transform of G? Well, the Fourier transform of any function, the L infinity norm is bounded by its L1 norm, okay? But its L1 norm is uniformly bounded, again, by the same reason, by this inequality. L1 norm is uniformly bounded. So these terms here are always O of 1. So you can even just say that this is less or equal than some constant, let's say some constant A divided by 2, just this bit. But, and then there is the big idea. These terms would be 0 from some point on, because G delta is supported in the interval minus delta delta. So what's the n that this summation have to stop? Well, it has to stop when this is greater than, in moduli greater than delta. That will be exactly when n is about e to 2 pi delta. So I can only summate this up to e to 2 pi delta, okay? Because the remaining terms will be 0. And those which are non-zero are just bound by a constant. And then I have this. Okay, there are better ways of bounding what we're going to do next, but one simple way is just to bound the von Mogul function by log of n and don't care about it. Okay, and then if you estimate the sum, it will leave an exercise. You can estimate by, let's say, the integral test, just compare with the integral of the function you're summating. So they would be another constant, let's say, prime delta e to pi delta. And the only thing you have to use here is that the primitive that d dx of square root of x log x minus 2 is log x over square root of x. Okay, that's why we get the delta. That's why we get the pi here, pi delta instead of 2 pi delta, because you have a square root here. Okay, and then you have a log. So the log of this number would be just delta. So that's why we get it. Okay, which is good because in the same size what I derived before, so it's still good. And what else? There is a better way of bounding this without doing this very crude estimate, and then you can even remove this delta from here and just have this bit, but I'm not going to do it. And the final term, T2, oh, let me just write it, will be a certain integral, minus 1 over 2 pi, integral from minus infinity to infinity of h delta of u, and the real part of gamma. Gamma 1/4 plus IU over 2. So note that I'm not doing anything fancy. I mean, rather than just bounding everything just by putting the moduli inside whatever and just brutally bounding things. I mean, it's going to work anyway. And in here, what you can do, so what is H? H is this guy here. So there is a translation here involved. So if I change variables, I can put G here. So you can put G, let's say, of V, and now this guy is going to be T minus V. And it's going to be dV. Okay, and t is going to infinity. So then I can use Stirling's formula to say that this is minus 1 over 2 pi, integral from minus infinity to infinity of d delta of v, and this is going to be log t, again, another one of these exercises, and log of 2 plus moduli of v dv, and this is an application of Stirling's again. Okay. So then you see that you have G delta integrated against this thing. Again, G delta is uniformly bounded by something like decaying like 1 over v squared. So when you integrate again the weight, it's going to be okay. You can integrate and everything is going to converge nicely. It's going to be just a O of 1. And then you have the second part, which has a log of t in front of it. So that's what we get. So we get the a minus log t 1 over 2 pi integral of g delta v dv plus O of 1. Okay, so now I have bounded all the terms. And then it's easy to, and then what we deduce that this thing was equal to less or equal than some a plus some b delta e to pi delta minus log t 1 over 2 pi integral from minus infinity to infinity. Okay, or this a here could be different from the a before, etc. Okay, so then if I add a log here and an O of 1 on the left-hand side, if I add a log t and an O of 1, I would get zeta. And adding log on the right-hand side, I have to did I divided this before? Yes, I did everything wrong. I shouldn't have this, sorry, I used the formula without this a half, so I should erase it. I used without this a half. That's what I did only. Okay. So if I divide by half, then I should have a 4 pi here. Okay, sorry. So if I add here a log of t and I add a O of 1 on this side, this would become a log of zeta of a half plus it. And this whole bit, and then I have to add here a log of t plus a O of 1 as well. So then I deduce that this thing is, so log of t, I can put this log of t inside the integral because of the fact that the integral of f is 4 pi. So you call the f is that the log of 4 plus x squared divided by x squared. You can compute this integral, and the integral of f is 4 pi. So I can include this in the integral, and then in the end, it concludes something like that. And maybe these a's and b's are different from the ones before, but anyway. Integral from minus pi to infinity of f of x minus g delta of x dx, which was the lemma. Okay. So just to recapitulate, what we did was we had a certain summation we want to estimate. We bound this summation by below from above by using this auxiliary function g, which I prove I can use the Guinan-Weil for this. Then I have 3 terms. You can just brutally bound in without thinking too much. And then in the end, you get the lemma. Okay, so we're almost done. Now we go to step 3, which is the final one. Okay. So now I have a problem. So what's the problem? I want to I want to minimize this integral among G delta in P-Levina 1 to pi delta, and satisfying an estimate of this form. Okay, so what you can do is simply, well, let's forget about this thing here, and just let's bound from below, and let's find the optimal one that minimizes this, and let's hope that this optimal one will satisfy the lower inequality, okay? And this turns out to be true. So, so I want to state a theorem, which I want to prove. So maybe I will prove it after we do the Branges stuff, because it will be related. Theorem is the following. If you have a sequence of numbers, say AM, BM, okay, let's say M in some translation over the internet. So what, before I state it, so what I want to do is to build this G, okay? And it turns out that the best way to build this G is to interpolate this G with the values of F, okay? So you select, let's say the integers or a translation of it, and you will make G to coincide with F at this translation of integers, and also the derivatives of G to coincide with the derivatives of F at these nodes, okay? And that will actually work. That function will end up lying from below, and then it will end up minimizing the norm, okay? So if AM and BM is just a sequence belonging to, say, LP, I will state the theorem in general, it will work for LP. So they're both sequences in little LP. That means if I summate get something finite, then the function, let's say f of, and we index by the sequence, let's say A, B, comma, Z. So suppose that this is a sequence A, B, which I would define by this. So summate over this translation. Theta could be anything here. It could be any translation of the integers. Again, this is exactly the same formula that I presented before in the Hilbert inequality case. I'm just remembering, and also saying that it works in LP and it works for any translation of the integers. Then this function belongs to P-Levina P of 2 pi delta, okay? And you have just prescribed the values of F and F prime at these points, okay? And the theorem is also vice versa. If you have a function P-Levina P, of course, P here has to have some condition on P. So let me put here, P has to be greater or equal to 1 less than infinity. Also, if you have a function in P-Levina P, then these function values here, they also belong to little LP and little LP. Okay, so it's a come and go. So that means that you can prescribe a function in P-Levina space 1, which is the one I'm interested here, just by function values. So it turns out the function we want is G delta of X is given by just the F. And then what's the sequence of A's you have to put? Well, you have to put this log sequence. That would be the first guy. And the second guy would be the derivative. So you use the formula above for this guy. And the correct thing to take is this translation, Z plus a half. Okay, and then I should also specify delta. So it should say delta here. Delta. Okay, so use that formula. And it turns out that this is what it looked for. Now, of course, but of course you have to show, so you have to show that it has all the needed properties. So you have to show that it has the needed properties. Of the lemma above. Okay, what was the lemma above? Let's go back. Well, the only one we needed was, well, two we needed was to, it indeed lies below. We have to still to show that interpolation formula won't give you that automatically. That would be the hard part. And also to show that this lower bound is satisfied, which will like be a byproduct of showing that this is less or equal than that. Okay. And heuristically, why this will work, which is more or less the same way we had before. So we have this function f. This is my function f, and I want something that lies below. So heuristically, what I'm doing is this: whenever I'm touching it, I'm touching also with just one derivative coincide, not the second. So we will bounce back. So whenever I touch, I bounce back, and then I bounce back, and so on. So basically, if you show that this thing starts at any point is below, then it will be at every point. So realistically, that's why it will work. And but the same could be true if it lies above. So a priori, you don't know if it lies above or below, but you have a guess that it will lie in one side of the function, above or below. And then you have to guess what is the correct translation to interpolate, and it turns out it has to be a half. Okay. And then, okay, so I'm not going to prove that because it's a very technical paper, but I can cite what the paper is the sequel of the previous paper I cited for the Hilbert type inequality, which is some extremal functions in Fourier analysis. And this is by Carneiro, which is my former advisor, and Waller, his advisor. And this is about the same time of the Saunders and Johnny paper, the result I'm explaining now. So the two papers came out at the same, more or less the same time. Okay, so the first one with the application number theory, and then the other one with the needed auxiliary functions. Okay, so then if you build it, one can show, then we're almost there. Then one can show that you can compute the norm explicitly. And that would turn out to be just 2 log 2 plus some 0 of 1 when delta goes to infinity, delta. As I mentioned, you should always imagine the delta goes to infinity. So if I put that back, I get that the log of zeta, put it information back, going to be less or equal than some constant a plus some b delta e to pi delta plus 1 over 4 pi the integral, but the integral now has this thing, this 2 over log. Oh, there was a log, maybe I forgot the log here. There's a log multiplying here, of course. There's this log here. There was a log multiplying the integral. So there was a log t, and then times the integral, which would be 2 log 2 over delta plus a little of 1. Okay, so that's what you get. And you get this for any choice of delta. So then now you choose a clever delta. And the clever delta to choose, it has to go to infinity and grow at the same time as t grows to infinity. And the clever delta is this log t minus 3 times log t. Okay, so if you choose that delta, then you can do a computation. It will leave as an exercise that it would be, well, these terms here will grow anyway, and you can bound these terms here will, this guy here will grow slightly slower than this guy here. Okay, so you will be able to include this in this little O of 1 here, but it will leave as an exercise. Then you can show that this is less or equal than log 2 over 2 plus a little O of 1 log t divided by log t. You can already guess this by my choice. This delta grows like log t. So I have log t here, log t, which was the term that I wanted. I have I'm dividing this by pi, so I'm canceling this pi here. So I just have this 4 and this 2. So I have a 1 over 2 log t, log 2 multiplying. So that would be the multiplying constant. And I have a log t divided by this log t coming from the delta. And then I have to absorb these other terms here in this little of 1, which I'm claiming you'll be able to. Okay, just slightly would be able to. But anyway, that would finish the proof. Okay. Any questions in this final step? Comments?
Yeah, I have a question.
Yep.
Could you please scroll up in step 1?
Yes.
We bound fx by c over 1 plus x squared.
Yes, this guy.
We only need this bound whenever the absolute value of x is greater than 1, or
yeah, we need this bound in general. So I'm saying this is bounded by this, some constant.
but fx seems explode and arranging.
Yes, so let me do it here. So f of x is log, let's see, maybe I'm wrong, let's see. So it's log of 4 plus x squared divided by x squared. So if I divide this, it would be 1 plus 4 divided by x squared. So when x goes to infinity, this would be growing like this, and x goes to infinity. And
Yes.
then when x goes to 0, this is exploding. Yes, you're correct. This is exploding. So yeah, so maybe I should put in here. Where did he put this? Put this at some place. Thanks for noting that. So thanks for correcting this.
Okay, thanks.
So this is 1 over, let's say 1 over x squared. Maybe 4 over x squared, but let me just put the cost. Let's say x greater or equal than 1. Which is all we need in the end, by the way.
Okay.
Yeah, so let me go back to the, yeah, there is. So this drawing is completely wrong. It should be something blowing up. And this is the function. This should interpolate. So maybe it should draw a better picture. Pulls up. Terrible picture. Anyway, something like that. Cool. Draw everything. Yeah, you have any other question?
Yes, I have another question. That's in the last in our last class, in the proof of theorem D,
Yes.
when we use 1 to deduce 2, and we bound the LP norm of G epsilon by the L1 norm of G epsilon and a L infinity norm. Why could we do this? Could you explain?
Sorry.
One more times.
Oh, up. You say here? Here?
No. I mean last class in the proof of
Last
theorem.
class. Okay.
Yeah.
Oh, yeah. So let me maybe you can ask that after I stop recording, maybe.
Okay. Thank you.
Yes. Yeah. But do you have any questions about the proof of this class?
No.
Great. Any other questions about this class? Great. So yeah, so I think so. I'm just thinking about this thing. I think that wouldn't be a problem. Let me just go between everything. So this should be only for x greater or equal than 1. So this is Taylor-Wiener. Okay, this is okay. So the max is at there. Blah blah blah. This is still true. Yeah, I guess it won't be a problem. But if you find any problems with that assumption, let me know by email or something. But I think it won't be. Anyway, okay. So if you don't have any problems, then I'll stop recording. So see you next Tuesday.